Okay, so it's been a while since we had our physics class, and the last time we started talking about electric charge, right? So the flow of charge, right? A charge produces current, and the flow of charge is what electricity is. Charges can be positive and negative, and as you know, like repels and opposites attract. So if you've got two positive charges, they're going to repel each other, and if you got a positive and negative, they will attract. Obviously, if you got two negatives, then they'll also repel. We talked about static electricity. We shared a video or two videos about that. We talked about how the atom is. So the atom has a nucleus with protons that are positively charged. We got neutrons, and then around the nucleus we have electrons that are negatively charged. And in an atom, right, to start off with, we have the same number of protons and electrons. Conductors are materials in which electrons can flow, right? And so metals are very good conductors of electricity because they have delocalized electrons that can flow throughout the structure of the metal, right? Carbon in some cases can conduct electricity, for example, graphite, which is made of carbon. Insulators are materials that do not have electrons that can move freely, and so they do not allow charge to flow, right? And when friction is applied to certain materials that would otherwise not conduct electricity, some electrons are sort of knocked off the atoms, and so they develop a charge, and that's where you get static electricity from. Now, when we're talking about good conductors and insulators, you've got good conductors and good insulators. So, materials that conduct very well and materials that don't allow electricity to pass through, and they do a very good job at that, right? Such as plastics. So that's nice. But then you've got stuff that's in between, and they are poor insulators as well as poor conductors. So they don't exactly stop electricity from flowing through, and they don't allow it to go through very well either. So it's somewhere in between. And materials like that are wood, paper, and cotton, and the earth and the human body. Talking about pure water in itself will not be conducting electricity. But if you've got any dissolved materials in there that form ions, right, then water will be conducting electricity because of those ions. For example, if you use salt water, so seawater will definitely be conducting electricity. Then we have electric fields, which is a region where an electric charge experiences a force, right? And it is a non-contact force because you don't need to be touching to do that. And the direction of electric field at a point is the direction of the force on a positive charge at a point. So it goes from positive to negative, right? And so if you throw a positive charge into an electric field, it's going to be deflected. It's going to be repelled from the positive side, move towards the negative side. Similarly, if you, right, so that is the benchmark for the definition. But just for the sake of explanation, if you throw a negative charge into a field, it's going to be deflected from the negative and move towards the positive, right? Because likes repel and opposites attract. But the benchmark for the explanation or the definition is a positive charge, right? So the direction of the force on a positive charge at a point, that is the direction of the electric field. And then we finally talked about, you know, uh, how the charges appear. So if you've got a positive charge, you have the charge sort of moving out, whereas a negative charge, the charge is moving toward. Okay, and so that's why it's going from positive to negative. Uh, and then static electricity occurs with non-conductors, right? And the reason why it's called static is because if a charge develops, it's not flowing, so it's in place wherever it develops. And so it's stationary, which is also called static, right? So not moving in place, and that is why it's called static electricity. And fields, whether we're talking about magnetic fields or electric fields, they are vectors because they have magnitude as well as direction, right? So they are vector quantities. Any questions?
No.
Okay. Now with that recap, today we are delving into a new chapter, 4.2.2, which is termed electric current. Okay, so what is an electric current? An electric current consists of a moving electric charge, as we mentioned, and we just saw in the recap as well. Now there's some explanation about an experiment to measure electric current using a Van de Graaff generator and all of that. I'll come back to that later. All right, so first let's talk about the the ampere and the coulomb. All right, so an electric current, to define it properly, like very scientifically, a proper definition. It is the charge passing a point excuse me, per unit time. And so that can be given as an equation, I equals to Q over T, where I is the electric current and Q is the charge and T is the time. Right?
Yes.
And what this tells us is that a current, electric current to be particular, is actually the rate of flow of charge in a circuit. Okay, is any of this making sense?
Yes.
Okay,
Um, can you explain that again, though?
which part?
Current is the rate
It's the
of.
rate of flow of charge. So Q is the charge and T is the time through which it flows, right? So in that case, you can also call it the rate of flow. Rate means how much is flowing per unit time,
Oh, okay.
right? So it's basically another way of saying the same thing.
Yeah. Okay.
Okay, the unit of current is the ampere. Ampere. It is given by the symbol A, right? And it is measured using a device called an ammeter. An ammeter. Okay, and just for context, a milliampere. So milli is 1000, right? Is 1000. 1000. That's 1 over 1000 of a full ampere. To make this make sense, right, we know about measurements, meter, centimeter, and millimeter.
Yeah.
So 1 meter is greater than 1 centimeter, and 1 centimeter is greater than 1 millimeter. In context, you got 1 meter. 1 centimeter is 1/100th of a meter, and 1 millimeter is 1/1000th of a meter. Okay.
Yes.
So just to put that into context so that's easier to understand. Okay. Now, along with that, we want to talk about the coulomb, right? Now, these two guys are like ampere and coulomb interrelated, right? The ampere, the current is defined as the flow of charge, right? And the unit of charge is the coulomb. Right, which is given with the symbol C, right, a capital C. And it is interesting because they're both related. It is defined in terms of the ampere. So what is the definition of a coulomb? 1 coulomb is the charge passing at any point in a circuit when a steady current of 1 ampere flows for 1 second. Right now, since we know this equation, we know that I is electric current and Q is charge. Can we rearrange this to get charge, an equation for charge?
Yes.
What would we get if we want to make charge the subject of the equation?
Q and I and
Hmm?
I and T. I
Sobia?
into T.
Sobia?
Yeah.
Yeah, what?
I was about to say the same thing.
Uh-huh. Okay, so if we rearrange the equation we have for current, then we get Q equals to I multiplied by, right? So current multiplied by time. So if we got 1 ampere flowing for 1 second, we get 1 unit, like 1 coulomb of charge, right?
Yes.
Now, it is very important that current must have a complete path to flow, right?
Yeah.
So right? If it does not have a complete path, an object might become charged. For example, if you've got a metal rod with a plastic handle and you're holding that, right? And this is metal. And so if this becomes like, if you zap it and it becomes charged, right? Well, actually just one. If it's got both, will just be like, it becomes charged. Then because it's the plastic handle, you're not touching it anywhere else, right? It will maintain the charge because it's not able to flow anywhere else, right? It's a plastic handle, plastic is insulator, it's not allowing the charge to flow, it's not allowing current to pass anywhere else, right? Whereas if you've got a complete circuit from point A to point B, right? And so current will flow through all of that. Okay, so if for example you were to hold this charged metal piece with your hand, then despite being like a poor conductor, the human body does allow the charge to flow through, it does allow current. So from the metal the current will go into your body, and then if you are don't have rubber shoes or slippers or something on your feet, it will flow into the earth, right? And so it's going to give you depending on how the its magnitude, it's going to give you a shock, right? Okay, so far so good.
Yes.
Can you please explain that?
Which part?
Uh, the thing you were saying right now.
You need a complete, like for example, if you want to go somewhere, you need the roads to be open, right? If the roads are closed, then obviously you can't get to where you want to go. So current also needs a complete path or a complete circuit, right, from point A to point B to be able to flow. If there's a block over here of some sort, then the current won't be able to flow. And so what will happen is that the charge will be held in this part if you are charging it, right? As soon as anyway the charge gets some path, whether the block is removed or it gets an alternative path to move, the charge will move that way. That's what I'm saying. Okay.
Yes.
Just like you're stuck in traffic and the main road is blocked, and then you take the side roads and the perhaps go into the gullies and all of that, find a way around the block. Similarly, otherwise you keep standing in traffic for however long it takes for the obstacle to be removed.
Yeah.
Okay, so I'm going to take you to the book for a moment, and I'm going to show you the experiment with the Van de Graaff machine before moving on. All right, so here they got a Van de Graaff generator which generates a charge, and then they've got these two metal plates. Okay, and they've got it connected to a pico ammeter which detects like very like pico is you've got milli, then micro, then nano, and then pico, so pretty small. Okay, and right, so there's charge on these plates, right? One of them is negatively charged and the other is positively charged. And then you got this ball, this tennis ball as they call it, and it has a coating on it, right, that is able to make it conduct. So the tennis ball itself is made of rubber, it's not a conductor. They've coated it with a material that's able to conduct. So what happens is the tennis ball moves towards one of these, right? So one of these is positively charged, the other is negatively charged, and they're apart. So the current is not flowing through the air because the air is a very good insulator, right? So it's not going to allow current to flow. So what's happening over here? The tennis ball touches one of these plates. Let's say the plate on the left is the negatively charged plate, right? As soon as it touches the negatively charged metal plate, it develops a negative charge. Now what's going to happen? Because the ball and the plate now are both negatively charged, it will repel. And when it repels, it moves towards the other. And because it's positive, the other one, it touches that plate, and there's a reading because current flowed, right, between the negatively charged ball and the positively charged plate. Okay, there's a reading. Now with that, when that happens, then it becomes positively charged. It's pushed from this plate, right, because it's being repelled, goes to the negatively charged plate over there, subtracted, touches that plate, you get another reading on the device. And so this is just an experiment to show how current, you know, how charge is carried, and only when charge is carried from, positive to negative, then you're going to get current. Otherwise you're not. Like, this plate can be positively charged, this plate can be negatively charged, but if there's nothing in between to carry the charge, there's just air, which is an insulator, then you're not going to get any reading because there's no current flowing. Okay.
Yes.
Okay, and all of that is detailed over here. Okay, let's go back. Now, what are the effects of an electric current? So if you have an electric current that's flowing, how can you detect or notice that there's an electric current that's flowing? So the first effect is heating and lighting. So normally you have electric currents in electric circuits, right? A circuit is different components with electricity flowing through them, right? So you've got positive and negative, and you got electricity flowing through them and all that. And you got maybe a bulb over here, and something else over here, and something else over here, and so, right, that is an electric circuit. So one effect, and it's illustrated in the book, is heating and lighting, right? And so the current that is flowing causes a lamp that is connected in the circuit to light up, and it also becomes hot. The next effect, the second effect that you would notice, is a magnetic effect. So we talked about electromagnets, remember?
Yeah.
That electric wire can be wound around a piece of iron, and when electricity passes through it, the wire, it will cause the piece of iron to become magnetized. So
Yeah.
even if you don't have a piece of iron in a simple, like, wire that is conducting electricity, there is a magnetic field around that wire as well, right? So electricity and magnetism sort of go together. And so, right, when there's current passing through the wire, it's going to have a magnetic field. So there's a magnetic field around an electric wire that is conducting electricity. Make that, like, if there's no electricity flowing in the wire, there's not going to be any magnetic field. When there's electricity passing through the wire, that's when you're going to have an electric field, right, which can be detected by a compass. So if you place a compass near a wire that has electricity flowing through it, you will notice a deflection in the compass. It will point towards, right, the wire in some way. And so that's a magnetic effect. And the third effect is a chemical effect. And since we've done this in chemistry, remember electrolysis,
Yeah.
right? What was the whole point of electrolysis? Electricity being passed through, substances to separate their ions and all that, right? And so if electricity is flowing, right, through a chemical, in this case they've given dilute sulfuric acid, then you will notice bubbles of gas being given off. So I'm going to ask you a question about chemistry. Bubbles of gas given off from sulfuric acid. Do you remember what type of electrolysis this was? When were we doing electrolysis of sulfuric acid? Anything?
Sir,
Anything?
Haram has raised her hand.
Is she?
Can you please wait for a second?
Sure. So the example they give in the book of how to notice the effect of electricity is if electricity is passing through sulfuric acid, you will notice bubbles of gas being given off. Right? My question is, this is obviously they're talking about electrolysis. They're not using the term electrolysis, but that's what they're talking about. What type of electrolysis is this? Passing electricity through sulfuric acid and getting gas as a product.
Electrolysis of water.
Yes.
Electroplating.
Haram, could you repeat that?
Electroplating.
No, not electroplating. It is the electrolysis of water. Right? And because water is not a good conductor of electricity, as I mentioned, on its own, right?
Actually, it's a poor conductor of electricity.
Right. And so what they do to have electricity pass through water is they acidify the water by adding sulfuric acid to it. And because sulfuric acid has ions, it has the hydrogen ions and the sulfate ions, the positive and negative ions. Those allow electricity to pass through. When electricity passes through, you end up getting both hydrogen gas and oxygen gas, right? So the chemical effect of electricity or electric current that they're talking about is the electrolysis of water in the example given. But obviously, electroplating, etc., all of those are also because an electric charge, a current is flowing through the system. Any questions?
No.
Okay. Now, what about the flow of current? Right? We're going to talk about what they term as conventional current, right? Which is basically the flow of current. So in a circuit, right, the current flows from in the direction of positive to negative. Which is what we've learned, right? Just like from the north to the south pole in magnets, current goes from positive to negative. So that makes sense. But the electrons flow in the opposite direction. And there's obviously reason for this, etc., right? So not going into detail, because this is all they mention in your syllabus. The only thing you need to know: conventional current flows from positive to negative, and electrons flow from negative to positive, right? Which is the opposite direction
Of current.
of conventional current.
Yes.
All right.
Yeah.
Okay. The next thing is really simple, right? I'm just going to uh, measure in passing. So we talked about the ammeter, right? An ammeter, right, is the device used to measure, right, current. There are different types of ammeters. They have different sensitivities. Sensitivity means how small of a current they can detect. So when we saw that illustration for the Van de Graaff, you saw what they had was a picometer, right? So milli is 10 to the power minus 3, micro is 10 to the power minus 9,
What's the
sorry,
difference
minus
between
6.
uh ammeter and picometer?
Not picometer, sorry, picoammeter. Picoammeter. So milli is 1,000, micro is millionth, nano is 10 to the power minus 9, I believe, and pico should be 10 to the power minus 12, if I'm not mistaken. Right, let me just check that. Yeah, so it is 10 to the power minus 12. Right, so that is small. That is 1 divided by 1 followed by 12 zeros. So 9 zeros is a billion, and that basically means this is 1 trillionth of a meter, of an ampere, right? So very small. So sensitivity, right? You can have a milliammeter, right? You can have a picoammeter. You can have a variable ammeter where you can adjust the sensitivity, right? So variable, where you can adjust it. You can also have something called a multimeter, which is able to detect other quantities that are related to an electric circuit other than the ampere. So it is able to detect the ampere, it is able to detect the resistance, right? Give you a value for resistance. It is able to detect the voltage, for example, right? And they can be analog or digital. So they can be the ones where they've got numbers and there's a needle pointing to it, or it can be one where they've got a display and they're giving numbers on that display, right? So they can be both analog and digital. Any questions about that?
No.
Right, and they can also measure current as DC, which is direct current, and AC, which is alternating current. Which is exactly what we're going to talk about right now. It's pretty simple. direct current, right? Currents flow in, electrons flow in one direction. Whereas in alternating current, right now you can have, a steady, before I move on to, or you can have a steady direct current or an alternating direct current. Basically what that means is, in this case, means you're changing the value of the current. Then you have, right, alternate direct current should not be confused with what is called alternating current. That is different, right? This is called DC, this is AC. And alternating current, the direction of flow of the electrons reverses at regular intervals. Okay.
Yes.
So because this is happening, and right, I'll show you the graphs for it. What happens is you have something called the frequency of AC, or alternating current, right? And that means the number of complete alternations, the number of complete alternations is coming from the word alternating, because it's going, right, it's changing direction, so it's alternating. So number of complete alternations of current or cycles of current per second, right, per 1 second. This is similar to, right, just to draw an analogy, the frequency of waves. Remember we talked about waves and the frequency, right? So number of complete waves per second is called the frequency of the wave, and it is given as hertz. The frequency of an alternating current is also given as hertz,
Right.
right? And it's given as the symbol capital H and a small z. So for example, if there are 2 cycles per second, that would mean the frequency is how much?
Mm.
Hmm?
It's 2 cycles, right?
Yeah.
Right. Okay, can you give me a minute? I'll calculate.
You don't need to calculate. It's pretty straightforward. What is the definition of the frequency of alternating current? There is no calculation required.
Number of complete alternation.
Or cycles per second. Right? Number of complete cycles per second.
Frequency is
Right? So if it's number of complete cycles per second and you've got 2 cycles per second, then the frequency is 2.
2 hertz?
Yeah. Like I said, you don't need anything to calculate over here, just like straightforward. Okay?
Yes.
I'll just show you the graph as the illustration for this in the text. So here we have the illustration. Right, so these two graphs on the left, top bottom, right? This is the graph of a steady DC where you've got one value of current, direct current coming in, and so you can get a flat line, right? But it's not at zero, it has at whatever value of current there is, and it's not changing over time, right? So current versus time, you're getting a flat horizontal line at whatever value of the current it is being supplied. Alternating or varying, right? Varying DC, you can see it starts from zero, it goes up, down, up, down, up, down, 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 and then, right? So that's varying. So I believe I wrote alternating direct current, right? I'll change that to varying direct current. Alternating current, you can see that it's constantly flipping and regular intervals. So you've got it's going the flow of the current that's positive and then negative.
Can we say that the alternating current is not regular?
It is regular because it is changing directions regularly. So,
Okay.
so, so there is regularity to it.
Okay, so we can just the direct current is not regular.
It depends, right? If it's just one value of current throughout, then that's steady or constant DC, right? If it's changing, then it's varying. So, I mean, I'd not try to forcefully use the word regular over here.
Okay.
Okay, so you can see that, right? It starts, goes one way, then goes the other way, and then comes back. And so this one way and the other way and back, this is one cycle. This happened in half a second. The other half second, another complete cycle. And so in 1 second, you have two complete cycles of alternating current, right? And
Yeah.
that means that the frequency of the alternating current is 2
2 hertz.
hertz, right? And so if you connect an ammeter to measure DC, it is only deflected one way, or it only gives you one value because current is only flowing one way. Electrons are only flowing one way, right? But if you connect it to a source that has an alternating current, then the pointer will move back and forth. Why? Because the electrons are changing direction of flow. So they're going one way, and the pointer will give you the needle will move to one direction if it's an analog ammeter, and when they change direction, the needle will flip back. Now, this flip of the needle, this movement of the needle is only visible if it's very slow, right? If the frequency is high, right, and the direction of the electron flow, the alterations or the alternations, not alteration, but alternations are very quick, then the needle can't keep up. It's not going to move extremely fast. It's going to be like there's obviously a limit, physical limit to it. And so the needle will appear not to move. It will appear to be in the center at zero, right? Does
Yeah.
that mean the value of the current is zero? No, right? It just means that the frequency is so high that the needle appears it's to be not moving, right? Where do you get DC from? Batteries. So your regular batteries give DC current. So the ones you put in your remote or other stuff. Generators can produce DC or AC, so it depends on how they're made, and maybe they have a switch to change from DC to AC, whatever that may be. Okay.
Yes.
Okay, so the next topic we have is electromotive force and potential difference. And so, right, I'll see you guys next time for that.
Okay.
All right.
Allah Hafiz.
Allah Hafiz.
Love is
Allah Hafiz.